Okay, so this week we are going to be talking about chapter 7 of the book, Techniques for Machine Learning Applications. So today we're going to build on what Chantal previously presented in the last 2 weeks, which introduced some machine learning techniques. And this week we're going to be looking in a bit more detail at particular methods and specifically kind of the typical or common stages of machine learning analyses and how to best choose and deploy models to get the answers that you want. So overall here we're kind of looking at the broader strategy and application of algorithms rather than particular instances or particular methods. So in this discussion, I'll be covering four main areas. Firstly, like an introduction and to cover the learning goals of the chapter. Then we'll look at how the nature of the data and the variables that you're considering imply particular approaches or particular techniques might be more suitable. After that, we'll talk a little bit about the common analysis tasks that are common to workflows like exploratory data analysis and standardization of variables. And then we'll talk a little bit of following the chapter. We'll talk a little bit about how to select models for a given scenario using the example of the rabies data, like tying the theory into some practical examples. Okay, so there are three main learning objectives in this particular chapter. So firstly, we want to understand how to manipulate and prepare data for modeling. And that includes the idea of feature engineering, the process of transforming your variables into something that a machine learning algorithm or statistical model can use more effectively. After that, we want to learn how to select the most appropriate model for a given data set and question, determined, of course, by what particular type of question you want to answer and the form of the output that you want. And then lastly, we'll talk a little bit about a couple of the example machine learning algorithms, making this a little bit more concrete. So this chapter as a whole doesn't cover, well, unsurprisingly, doesn't cover all of the possible machine learning methods and modeling estimation techniques, but it does talk more about modeling strategy, like how to think about the problem and the data in a way that leads you towards the right approach. So what we're aiming for here, I guess, is to like come away with a sense of what's possible and when particular approaches might be more useful than others. So we'll first talk a little bit about how the goal of the analysis and how the form of the data that's available to you affects the possible choice of method and estimation strategy employed. So yeah, the first thing you're going to want to consider in applying one of these approaches is to define your goal. So you're going to be thinking about like what particular research question you want to answer or what output that you're looking to achieve. So typically this is like thinking about whether you want to explain a relationship between variables or whether you wanted to something that's a bit more predictive of new data. You might be that you want to explore trends over time, or look at how things are developing in the short, medium, and long term, and focusing on those kind of questions are going to influence your modeling approach and your choice of method. So let's say, for example, we want to model the effects of various factors on continuous outputs, like life expectancy. So it's not a binary outcome. It's something that is a number, and that number is continuous. And let's say we're looking at trying to explain the effect of various factors on that. So you might want to know like how, say, explanatory variables like lifestyle or chronic diagnoses affect continuous outputs such as life expectancy or DALYs. So because in a scenario where you are looking at explaining the result, you might want to consider like a traditional regression model where you can look at the size of the coefficients on your model and then understand like the effect and quantify the variation in the output that is the result of variation in the predictor variables. So in that kind of scenario, we are looking to like fit a relationship to the data, minimizing the sum of squared errors. If we wanted to, I suppose there might be a scenario where we would want to avoid overfitting or multi-collinearity, where we have explanatory variables that are highly correlated with each other. So if that was an issue, we might want to consider extending the standard basic linear regression model to something like ridge or lasso regression, where we, rather than just minimizing the sum of squared errors, we're also introducing a penalty term to the loss equation, where we essentially take a multiple of the number of parameters or the absolute so the some function of the coefficients. So with ridge regression, that minimizes the sum of squared errors plus a multiple of the sum of squared coefficients, which reduces the relative importance of smaller coefficients just by scaling everything a little bit down. And then lasso regression, I think, is a little bit further. That goes to minimizes the sum of squared errors plus the sum of the absolute value of the coefficients, and that can actually like reduce the smaller reduce the smaller effect sizes to 0. So in effect, does a little bit of trimming of the output and drops the less important coefficients. Okay, now if you contrast this with, I guess, a categorical or binary outcome, so this might be a scenario where the output is disease or no degree disease, alive or died, that kind of thing. So that kind of binary outcome where it's yes or no. If you could use a logistic regression if you were looking to kind of have an explanatory model. But if you wanted to something that was a bit more predictive, maybe you might want to consider a machine learning classifier approach, such as a decision tree or other algorithm. For more complex systems, so for example, the use of if you want to like model the spread of a disease, where you need to account for, say, the flow of people between various states. That might involve a more, essentially, a more advanced modeling. So it's not something as linear. That could involve, say, well, for example, in the SIR model, you are modeling differential equations. And in that kind of scenario, it's hard to like, I guess, fit those equations. So you would want to simulate them by iterating over various parameters to explore how changes in the transmission and recovery rates affect future values and better fit past data. And then finally, if your data includes like a trend or a season element, you might want to have a bit more of a traditional time series model, like an ARIMA model, which could be used for forecasting to include features like autocorrelation, where you're essentially setting your future values contingent on past values and modeling things like seasonality and trends explicitly. So yeah, as you can see, like the nature of your data and the particular aspects of the question that you want to answer has a heavy influence on your modeling decision and what kind of approaches that you follow. We need to think about, for example, like whether the outcome variable's binary or continuous, and also think about things like whether the input values, the input or predictor variables are correlated with each other, or if we need to reduce the number of features, or indeed add more features in, or that kind of thing. Now, if we I suppose if we used all those things are going to dictate what type of method we use. It might well be that there are still a number of options for algorithms that we can use, and that might you might have more than one acceptable model. But I guess the idea is, I suppose, if you're using a suboptimal method, then you're going to risk obtaining at the least imprecise answers, or possibly even coming up with the right answer to the wrong question, even if the modeling approach itself was, perfectly valid and satisfactory. Okay, so once we have the goals of the analysis set up and the choice of method selected, we can move on to the next steps. Often, like the next steps, I guess, are going to be contingent on what particular machine learning algorithm or method you are following. However, there are some common, typical features of analyses that are covered in the chapter, which are useful to consider. So, with all analyses, and indeed this is common to all sorts of analyses, not just machine learning approaches. The first step is usually to do some exploratory data analysis, abbreviated to EDA, and that's where we're aiming to get a basic understanding of the data, its shape, its structure, how many observations there are there any quirks in the data, before we start doing formal analysis with it. So we can start with looking at what variables you have available, and which ones you might want to use. And also noting whether there are any variables that are missing, that you would like to have but don't have. After that, it's usually a good idea to start with some descriptive statistics of central tendencies and variation, the means, medians, and measures of spread like standard deviation, to get a sense of like what the average values are. These summary statistics can be, I guess, augmented by basic plots. So one thing I like to do is always start plotting histograms of the key variables, and those are quite useful because not only do you get a visualization of the spread of the data, but also they're quite useful for picking out outliers. And yeah, if there's any kind of skewness to the data. So if I think it's like, if you've got say some data on healthcare utilization, and you wanted to plot age, then typically speaking, you're probably going to see more older people in that distribution because older people tend to consume more healthcare than younger people. And like the size of that effect can be you can get a feel of that by doing plots. And then lastly, you might also want to consider looking at correlation plots, particularly for your input or predictor variables, just to see whether there's any variables that are highly related, highly correlated, I should say, because those it might well be that you're not adding any additional information by including more than by including lots of those variables if they are highly correlated, and therefore the variation in the output is adequately explained by one of those variables rather than adding lots and lots of them. If there are variables that are highly correlated, then I guess you also running a risk of overfitting if you include lots of those kinds of highly correlated variables. Once you are at the stage where I guess you feel you've got a good understanding of the data, the next step's often feature engineering, transforming variables into forms that are more useful for modeling. Now, that might mean something as relatively basic as taking logs of skewed variables if you want to reduce the amount of skew there, or just like binning ages into discrete categories rather than having them continuous. You might want to encode certain categories as dummies if your machine learning algorithm needs them in that format. And you might also want to consider if you need to create new variables from your existing ones. For example, if there's you're interested in including an interaction term to capture the effect of the interaction between two predictor variables, as well as having them on their own. So if you had a variable that was well, let's say like a high blood pressure diagnosis, and also one for a diabetes diagnosis, but you were also interested in how those variables, what the effect was if both of those were present, then that's, you might want to consider an interaction term, creating that and including that in the data set as a new predictor variable. And then lastly, you might want to consider centering or scaling variables conditional on which machine learning approach you're following. So in kind of like classical regression analyses, you do sometimes center or scale variables. It doesn't have any sort of effect on the overall fit of the model, but sometimes it can make interpreting coefficients a little bit easier. And I guess for interaction terms, it can also reduce the size of the standard errors on those terms. For machine learning algorithms, that kind of centering and scaling can be a little bit more important, depending on which particular approach you are going with, because some of them can be sensitive to the scale of those input variables. So, without correcting them, normalizing them, variables with larger numbers and higher variability can dominate the model just because their absolute numbers are bigger. So that can be an approach. And sometimes, you might even have a scenario where you've got really big numbers that scaling the variables also helps or reduces the amount of time and processing power that you need that your machine or your laptop is using to return the outputs. So once you've carried out a bit of exploratory analysis and done any wrangling and feature engineering on your data, hopefully firstly you should understand the data and the problem a lot better, and you can hopefully have also improved the ability of the data set to explain or fit the data as well, and made the task of the particular machine learning algorithm you're using just a little bit easier. The remainder of the chapter considered some practical examples using a rabies data set, which we'll kind of walk through a little bit as well, because it's easier to see, I guess, how these things work in practice rather than just considering them in the abstract, as we have done thus far. So the second half of the chapter walks through an example of aiming to predict DALYs in the Asia and global regions using the rabies dataset, which is included within the package. The dataset covers, it's got 240 observations and 7 variables, so it's a relatively small data set. But it is possible to get some useful information out of this. It contains both all-cause and rabies mortality and DALYs for those regions, subdivided by year. And yeah, there's also like a upper and lower boundaries as well as estimates for those. So the first, like in the exploratory data analysis, the initial exploratory data analysis showed that the death rates and DALYs measures were kind of quite different in the magnitude and scale. So death rate being a rate would be between 0 and 1, but DALYs are much higher in that data set, as you can see. So a decision was taken to kind of to scale those so they were closer to closer together. I think to scale to like a 0 mean and a standard deviation of 1, which is the default behavior of the scale function. It was used, which is nothing in the base stats package. It's not a particular one from a particular epi package or anything like that. And then you can see, well, the chapter's got these graphs in them as well. But you can see that before you've got the death rates down there at the bottom, dwarfed by the DALY values up at the top, and then afterwards, after scaling, everything's around this 0 mean, and then also the distributions are a lot less variable, because you've got most rate, within 2 or -2 in there as well. Okay. There was also a little bit of feature engineering done by the inclusion of additional variables derived from the all-cause DALYs and death rates. So, yeah, that meant that we could use all-cause mortality as a possible predictor value, not just rabies mortality and rabies DALYs. That additional context was possibly useful to help the model distinguish like the specific signal of rabies from general health trends. And I guess allow like the predictive algorithm more opportunity to better fit the data. After that exploratory data analysis and feature engineering, a bit of feature engineering, the data set was split between a train and a test set. So training sets used for developing the model and cross-validating the results to tune the hyperparameters. And then you've got a 20% final test set, which is used to evaluate how well those model parameters fit estimate how well those models would fit unseen or new data. Cross-validation of the training sets was implemented using a 10-fold split, and that meant that the training set was divided into 10 parts, each fold held out as a validation set, whilst the remaining 9 were used to train. And that kind of cross-validation strategy means that you can I guess gives you a more robust estimate of performance rather than just testing it once on one particular holdout set, because with a small data set there's perhaps quite a relatively high chance that any particular sample may not be representative of new data, or indeed the final test set. Once those splits were made, then there was a little bit of pre-processing handled by recipes, which are like that's the I guess the way that the tidy models pipeline deals with these things. So you are essentially passing in like a recipe for pre-processing, and the advantage of that is that they can be piped in relatively easily and also swapped out if you want to change your recipes, and the whole thing is a lot more reproducible. It's, I guess, easier for understanding as well. There were 3 particular recipes that we used. Firstly, there was one which was just included all predictors, was all input variables without any transformations. That was kind of a baseline one. Recipe 1 added some dummy encoding for the categorical variable for region and standardized numeric variables. And then recipe 2 built on recipe 1 by also transforming the outcome variable, DALY's rabies, using the Johnson method. It's not something I'd come across before, but essentially that transformation makes the outcome distribution less skewed in the same way that a log would, but I guess probably does a better job. And by reducing that skew, we're reducing the possibility that there's like an issue in estimation there. It was also noted that multicollinearity was present in the data set, as kind of would be expected, because all-cause mortality is going to be at least partially correlated with like the specific cause mortalities, and death rates and DALYs are also like going to be likely to be highly like correlated because DALYs are partly a function of years of life lost, which is obviously correlated with mortality. So whilst this, could be dealt with separately, for example, using sort of like principal component analysis or some other method, in the chapter, it's dealt with by the choice of prediction method. So the two methods that are chosen, random forest algorithm and the generalized linear model with lasso penalty, they can both deal with that multicollinearity within the estimation technique. So they are robust to this issue anyway. But if if we were using a different method, then perhaps maybe we need to deal with it at this stage before we fed it into the model. Okay, so the first model that was considered was random forest model. So that, again, this is all with the tidy models framework, and then that framework allows you to tune the hyperparameters using tune grid function, and once that was all done, the optimal parameter combination was calculated as what do we have? We had number of parameters each split of 4, number of trees is 1794, and the minimum node side was 7. And then that gave us root mean squared error of 0.506, and then figure 7.4 in the chapter gives us a nice graph and shows the close relationship between the predictions and the observed data. So we can see it's all quite close, very close to that 45-degree line there. The second model used was a linear model using the package GLMNet. That converted the data into a matrix form to handle the dummy variables automatically, and then automatically tunes the penalty term parameter. That gave us the optimal lambda penalty term. I wasn't entirely confused. Wasn't entirely sure what that was. I don't know if this is like a typo thing or an issue with the issue. With like the particular seeding or whatever, but the text mentions that the lambda was 0.165, and then in the actual code it's 0.09. But yeah, I'm sure we can discuss that in a minute. But that kind of like puzzled me a little bit. But either way, it's certainly a lower root mean squared error than the random forest one. So on this particular tests or particular measure of model fit, then the GLM model we performed better according to that metric anyway. And then the last section of the chapter ran through a few other models, showed you how to use the parsnip package and workflow set to test more models, and it fitted some additional support vector machine models and k nearest neighbor approaches, and I think I've actually found that a Johansson transformed support vector machine model might even have improved on the GLM model. So I guess it just goes to show that you have to test a few of these things out and grade them accordingly. So I think so this that was everything. Just, I guess, to summarize. So this chapter looked at machine learning techniques as a kind of a holistic pipeline, not just on individual machine learning algorithms or methods. Um, the kind of there's a nice little summary at the end of the chapter, which I've just copied and pasted in there because I couldn't really improve on it or summarize it much further. Just it's a nice little just a nice little, I guess, summary of the various steps that you want to consider when running through each of these pipelines or attempt to apply a particular model. So yeah, I guess I just put a little summary at the bottom there. Say, yeah, it's not just about picking a model and plugging it into the code. You've got to kind of consider your goals, the analysis question that you're interested in, the features of the data set, and do a lot of like pre-processing and calibration work before you let the machine learning algorithm loose. Okay, so I think that's the end of the material that I wanted to cover. I will pause now, stop here. If there's any questions or any discussion points that people want to raise.
I have a couple of questions, if that's okay. First of all, well, I think that was a really good presentation. It was nice to have a good walk through and look at things. I think the first question I would ask is, in your sort of day job, do you use any of these approaches, or do you use them on hobby projects or anything? Do you apply them yourself?
Not I guess there's probably like less cause. Like for me personally, I think it's probably fairly rare um that I would tend to go for these things. So I've used random forests in the past in a previous job. But at the minute I'm more in the explanation rather than prediction game. So most of the stuff we do where we do need to do these things, we're going for like classical regression models where you can get a coefficient and say, well, x of one unit increase in x gives this in y and that kind of thing. Yeah, so when I used the random forest model in the past, I think I'd used it for just mainly actually for like being able to visualize like decision trees. Because that was quite a nice way of um putting the predictor variables in hierarchy. And there's a nice little package I think called rpart that allows you to like visualize like the effects of things. So I think this was like it was a project where we were looking at data delays. So you could say, if this happens, then there's uh, uh, an extra X minutes before the theatre starts and that kind of thing. So for presenting to a non-statistical or non-analyst group, those kind of visualizations were useful, and that was like, I guess, as much of a plus point as the accuracy of the prediction.
Okay.
Sorry, did you have a second question?
I did, and you've kind of brought me nicely
No.
onto it actually with what you've just said, talking about being able to explain these things to non-specialists and even to data people who perhaps have very little experience in the kinds of things that you've looked at in the chapter and in the previous chapter. Were there any models that you thought, yes, this could potentially be quite easy and transparent to explain the decision making, or this would perhaps be a lot harder, or maybe even not possible? Were there any examples of that? Because there's a lot of talk now about transparency, isn't there, around using machine learning and AI and with the general public, and certainly working in a local authority, there's a lot of misunderstanding, miscomprehension, and if we don't, well, not we as the data team, but if people in the local authority are trying to use these things and they don't understand, how do you then explain that to residents, to citizens? And so the question really is, were there any that you thought, yes, this could be quite straightforward to explain, wouldn't be too difficult, and others that you think, I have no idea how decisions are being made with these sorts of algorithms?
I suppose in some senses it's not necessarily the choice of algorithms only like a part of that discussion, I think. So whilst part of it is just how you I guess grade the model as well. So like root mean squared error means very little to somebody who doesn't know a lot about statistics, but something like a receiver operator characteristic might need a bit of explanation, but you can get how people will understand what a false positive is. And so that probably means that's maybe a little bit less work than talking about residuals whilst people's eyes glaze over. So I think it's multifactorial. It's not just necessarily about the particular algorithm. That said, I suppose people may be a bit more familiar with regression models just because they've been around longer, but it probably it depends on the previous experience of the people you're talking to. And I suppose the other thing is if you can get a decent sized final test set, or you can run your algorithm in parallel or in shadow for a period of time, and then you can build up a track record to say, well, we put this in, we did this many months ago, and we've been tracking it ever since, and this is what we found when we've tracked it against the real data. Then I think that kind of practical demonstration of how close you can get is probably worth more than or it's an easier way of demonstrating that than to non-technical audiences.
Machine learning is interpretive dance. No, thank you. That was very good. Thanks a lot.
Does anyone get any other questions? Federica, can I just check this lambda thing, because it was confusing me. I don't know if I've just not understood it right in the text.
Okay, which one? The okay, we can go back to that next time. So I'm gonna have the next section. So before to get started with the next chapter, I'll mention that a bit.
Okay, yeah, that's fine.
My question is to you: which model would you have used to instead of a random forest? In this case, that's personal opinion.
So I suppose the cop-out answer, but the honest answer, I suppose, is it would depend on the context within which this analysis is being done. So does it need to be? Are we just going for purely predictive accuracy, or are we going for something which can be explained to an audience, and therefore we need to have an understanding of what's going on in the black box. So I suppose if you're going if you go on predictive accuracy, then I suppose you could go for the lowest squared error. which I guess would be like the support vector machine that was tested at the end, in the last section. But then, yeah, then it's like as we said, it's a bit of a black box.
Yeah, but it's important to focalize what is happening when you apply a model, and so in this case, that was a way to, yeah. But, I think it's you're right when you said that the techniques I just mentioned, and that was a way to introduce like the tune grid into a model that could have be easy in some senses, easily understood what is happening inside and what is going to, so when you apply a model function and you search for parameters, calibration that is going to be the best one for your data. And what I asked myself, what was the best type of model that it could be able to let the reader visualize in some senses, grouping things and selecting those ones that are better for, I agree with you. And thank you for your summary of the chapter. And it's somehow difficult to make a selection of the best, because you can just throw things down and say you can do this, but then it might be important to understand what's happening behind those things, and then you, like, in the next chapters, then we're gonna be applying those things over and over and over again, or different case studies, or going back to the same data and apply those things in a way that, so the objective, the aim is to let the reader get into the topic and then be able to use it by itself. So
yeah, I suppose the other thing that comes to mind is that we normally we've talked about, I guess, accuracy in terms of like in a very statistical sense of like the size of the mean squared error, but the ultimate output, because it's like this difference between what is statistically significant and what is clinically significant. So it might be that 0.1%, 0.0001 improvement on the mean squared error actually means very little, clinically, or it might be that, increasing the accuracy by 2% means that, we save X number of a huge number of qualies or dallies, in which case obviously the value of a closer prediction differs. So again, I guess it's always like down to like context and what you're trying to do with the analysis, as much as grinding out those last few performance improvements. Okay, does anyone have anything else? Otherwise I'll just stop the recording, I guess.